Okay, this is section 4.8 on other discrete probability distributions in Statistics 341 Intro to Prob and Stat. By other, that means that we're adding to our already, accumulated knowledge of discrete probability distributions. The three discrete distributions we've studied to date are the Bernoulli random variable, or the Bernoulli distribution, the binomial distribution, as well as the Poisson distribution. So we're going to add to those three distributions three new ones. The three new ones are the geometric distribution, the negative binomial distribution, and the hypergeometric distribution. I'll do a short video on each of the three distributions, and then we'll finish with trying to apply distributions to specific settings by recognizing which distribution applies to a contextualized situation. So let's get started with the geometric distribution. So to build your intuition about the geometric distribution, here's a game you could play with a partner. A round would consist of the following actions. Using a cup, you roll a fair six-sided die without revealing the result, and then your partner tries to guess the result. And the question in this scenario is, how many rounds will be played on average if the last round played is your partner's first successful guess? So let's go ahead and see if we can apply some knowledge of probability to this particular problem. So do a little bit of math here on some paper. So let's go ahead and think about a random variable that we could define here. X would be the number of rounds played until, I guess, the dice is guessed, or until first correct guess. So the last round of play is a correct guess. So we would think then that X could take on values 1, 2, 3, 4, 5. And conceivably, this could go on for an extremely long time. So we could think of this as a random variable that has a countably infinite number of possible outcomes or potential outcomes. So what's the probability the game ends on the first, the probability that the game ends on the first round of play. So we're interested in calculating what's the probability that X equals 1 in this case. Well, if X is going to equal 1, then the guess must have been on the first round of play. There are 6 potential dice rolls, so the probability here must be 1/6. What about the probability that X ends on the second round of play? Well, in order for this to occur, we can see that we have to have an incorrect guess, so that's a 5/6 probability, followed by a correct guess on the last guess, a 1/6 probability. What's the probability that X is equal to 3? Well, here we'd have a 5/6 probability twice, because we've got 2 incorrect guesses followed by a correct guess 1/6 of the time. And then probability that X is equal to 4. Well, here we'd have 3 incorrect guesses followed by a correct guess. And now I can kind of see what's going on here. In general, we have 5/6 raised to a power times 1/6 always raised to the first power. So generalizing this, we can kind of see now from our examples above that the probability that X is equal to X is always going to be 5/6. Now that's going to be raised to 1 less than the X's value, so it'll be X minus 1 all times 1/6, which is the correct guess on the final, round of play. Here the support for the random variables distribution is 1, 2, 3 on to infinity. And it seems like we've discovered, a form for this particular type of a problem. And the question is well, what's the form's expected value? How many rounds on average do we expect to play, right? And so that's really what we've been asked to figure out is what's the expected value of this particular game. So let's see if we can go to the calculator to help us a little bit here. I'll go to the calculator, and for reasons that will become apparent pretty quick, I'm going to use the statistics editor, which allows me to input values into an Excel-like spreadsheet environment. And the first thing I'm going to need is a sequence of outcomes for the random variable. So I'll go to list operations and get sequence. The format for this is x comma x, or evaluating x, the expression x, where x ranges from, oh, why don't we do 1 to 100. So we'll go ahead and do that, and that gives me a sequence of values for the first 100, I guess, outcomes or potential outcomes of this experiment. The next thing we're going to do is we're going to calculate the probability that the game ends in exactly 1, 2, 3, 4, and so on rounds of play. So we have an expression from that for that, and it's equal to 5/6 raised to the, let's see, the value in list 1. So I'll do L1 minus 1. So that's our x minus 1, if you'd like, in the previous work. And then we have to multiply by the probability of a success, which is 1/6, and hit enter. It'll take it a second to do this because it's calculating it for 100 different cell values in list 2. And once that comes up, we can see indeed that looks like it's correct. It's 1/6, and you could check these numbers against those that we obtained in the handwork. So now we have a list of outcomes and a list of probabilities, and we know that expectation is the product of each of these rows summed for all possible x's. So let's go ahead and, well, I guess the first thing might be interesting to notice is that it does appear like the probabilities are going down in value the longer the game lasts. So in a sense, what's happening is we're asymptotically approaching 0. But thinking about the product here of, you know, values which are increasing in this column and decreasing in this column, it's not at all clear what the expectation will be for this particular random variable. So what we need to do at this point is multiply the two columns and take a look at that result. So I'll go ahead and let this be equal to L1 times L2. So I let list 1 times list 2, and I can see that indeed things are increasing until I get to around this region, and then we start, it looks like, decreasing from there and asymptotically approaching 0. So each, I guess, higher value of the random variable, since it has a small probability, it's contributing less and less to the expected value. I guess the last thing we'd like to do is sum all of the variables, I guess all of the values in list 3, to see if there's some sort of a limit to that sum. So that's what I'll do next. I'll go to my list editor and under operations pull in the cumulative sum. So that's number 6, and I'd like the cumulative sum of list 3. And what that's doing is literally summing all the individual values, the individual products, I guess, in the expected value expression for the first 100 outcomes. And now we have a cumulative sum of these products of the probabilities times the random variable's value. And if we scroll down through them, what we're looking for is to see if there's some limit to this, or if the expected value truly does exist. And you can see that the farther we go, now we're at the 34th outcome, things are now starting to slow down in terms of the change in the cumulative sum. And it seems like we're approaching a number, and that number seems to be 6. Let's just see if that's what happens. We carry this out far enough, we should see it actually converge to basically the machine accuracy of the computer. And it does appear that 6 is the limit. So based on numerics, I guess we can say that what we found here was that the expected value, it appears to be 6, which is curious, right? Because if you think about this, this is the same as 1 over the probability of actually winning on any one particular round. So the question is this thing equal to 1 over P, the probability of correctly guessing in any one round? This should sort of make sense to you because of the fact that you have a 1 in 6 chance of guessing on any one round. So it stands to reason that it would take 6 rounds of play on average to get a guess correct. So hopefully that's generated some intuition around this random variable. let's go ahead and formalize it, and then we'll come back and make sure that you understand what's going on here. I don't want to close that completely out. So here it is. It turns out that the geometric distribution, it has three requirements. You have to have independent trials. In the dice roll, we can think that, well, sure, dice rolls are independent. Each has to have a probability of success p, so that has to be constant. So, and that turns out to be true with the dice game as well. A constant probability of success is 1/6. And they're performed until a single success occurs. So that's the third requirement of a geometric distributions context. So if we let x be equal to the number of trials required, then the probability that x is equal to, say, some number of trials is equal to 1 minus p raised to the n minus 1. So this would be the probability of failure. In our case, that was 1 minus 1/6, or 5/6. And minus 1 failure is followed by a single success, so p raised to the first, or just p. The support for the variable is 1, 2, 3 to infinity, so it's countably infinite. We say that x is a geometric random variable then with parameter p. Notice that there's only a single parameter needed for this function to perform its task, I guess, which is to predict probabilities. You simply need to know the probability of success at any stage in the game. And it turns out that this particular random variable, the geometric distribution, does indeed have an expectation of equal to 1 over p, so that matches up with our intuition from the graphing calculator. I will say that I usually prove this fact in class when we meet in lecture. Since I'm not able to meet in lecture, I'll avoid the proof today for purposes of keeping this video short. But it is a rather interesting proof, and it is proved in your book, so I would just direct you there if you're interested in the theory why that actually works. Another important result is that the variance of x is equal to 1 minus p over p squared. So that gives you a sense of how much variability there is in the particular, I guess, result of the expected value. So let's go ahead and apply that and conclude with the geometric distribution with that application to our problem at hand. So what would the variance of x here be, and what would that tell us? So the variance of x, we're told, is 1 minus p all over p squared. So p in this case is a probability of success. That's 1/6. So 1 minus 1/6 all over 1/6 squared. And let's see, so that's 5/6 on top all over 1/36 on bottom. So it'll be, let's see, let's come down here. 5/6 times the multiplicative inverse of 136, which is 36 over 1. Sixes are going to cancel. So we get 30 as the variance, and the standard deviation then of x is going to be the square root of 30. So let's see, 30 square rooted is around 5.47. So what that tells us is that on average, it's going to take about 6 rounds of play, but the average distance from that, I guess, mean number of rounds of play is somewhere in the neighborhood of 5. So quite a bit of variability in this particular game. You kind of think of it this way: it's going to take you to successfully win on the game. An average number of rounds of play would be 6, but you shouldn't be surprised to win in 1 to about 11.5 or 12 rounds of play. So adding and subtracting this number to that number gives you a good sense of what's sort of average. So let's see, 6 plus or minus 5.47. You know, we could kind of just roughly say 1 to, let's say this is 6 plus 6-ish, 6 plus 5, 1 to 11. Well, let's just round it up to 12. 1 to 12 rounds would be a typical number of plays. All right, well, let's go ahead and end here, and I'll move on in the next video to take a look at the next random variable.